We've been working on modeling a structural regression model using data from a study on latent cognitive abilities of high school students. Latent cognitive abilities are those which cannot be measured directly, but which are manifested in ways that can be observed. Part of the model fitting process is assessing the fit of the model to the given data, and our initial model did not fit the data well. We then used residual analysis to answer the following questions. In what ways does the initial model not fit the data well? Can the initial model be extended, or can it be loosened up in such a way that it becomes flexible enough that it does provide a good fit to the data? Our residual analysis revealed that the primary problem the model was having was fitting the covariance between two particular manifest variables, V6 and V9. Based on this, we made a targeted change to the model by allowing the error terms of these two manifest variables to have non-zero covariance. This extension gave the model enough flexibility to provide a good fit to the data. In this lecture video, we continue our analysis and development of this structural regression model. Now that we have a model that fits well, we're going to look at two possible simplifications of interest. Our goal will be to determine whether this structural regression model can be simplified in these two ways without significantly compromising or degrading its explanatory or predictive ability. This modeling approach is consistent with the principle of parsimony, which says to select the simplest hypothesis or model possible from among those having equivalent explanatory power or predictive accuracy. So here's what we're going to do in this video. We're first going to review the initial structural regression model. We'll then take a look at the extended model, which is going to serve as the starting point for the simplifications that we're going to be looking at in this video. We'll then consider the following simplifications that are relevant in the context of this model and the theory that it represents. The first two simplifying assumptions will be considered simultaneously. Is it reasonable to assume that the error terms of the manifest variables are all equal? And second, is it reasonable to assume that the variances of the error terms of the figural relations latent constructs are equal? We're going to consider these two simplifying assumptions at a 0.05 level of significance. And finally, is the assumption of factorial invariance over time of the two figural relations constructs reasonable, again using a 0.05 level of significance? So let's get to it. So we'll first review the initial model. And so this is the path diagram for the initial structural regression model. And we can see here that we have 9 manifest variables in this model, V1 through V9. There are 21 asterisks and therefore 21 parameters to be estimated in this model. So we're going to call this initial model Model 1A. And in this model, we have 9 manifest or observed variables. There are 21 model parameters that need to be estimated in order to fit this model. The number of degrees of freedom associated with this model is equal to the difference between the number of non-redundant entries in the covariance matrix, which is p times p plus 1 over 2, and the number of model parameters to be estimated. And so the number of model degrees of freedom is equal to the difference between 9 times 10 over 2, or 45, and 21. And so this model has 24 degrees of freedom associated with it. Now when we fit this model, we saw that the chi-square value for the model was 52.0968. The ratio of the model chi-square value to the model degrees of freedom is 2.107, and that's quite large. Remember that we're looking for values of this ratio to be close to 1, and if they're quite a bit larger than 1, then that would indicate a poor fit. And so this indicates a poor fit of the model. Also, because we have this large ratio, we expect the p-value for the chi-square statistic to be small, and indeed it is, 0.0008. And so that's not a good thing either. Now the goodness of fit index, the GFI, at 0.9533 is larger than the midpoint nines, so that's a good thing. That would indicate a model that fits well. However, we've got these other indices that don't paint a very good picture. The adjusted GFI at 0.9124 is not greater than or equal to 0.95, and so again that indicates a poor fit. And finally, the root mean squared error of approximation at 0.0731 is not less than 0.05. And so that does not indicate a well-fitting model either. And so based on these model fit indices, we determined that the initial model did not fit the data well. Next, let's review the extended initial model. We extended the model by allowing the error terms E6 and E9 to have a non-zero covariance. And so you can see in this updated path diagram, we have a two-sided arrow connecting E6 and E9, and the asterisk indicates that the covariance between those two error terms is a parameter to be estimated. In this path diagram, there are 22 asterisks, and therefore there are 22 parameters to be estimated in this extended model. Again, there are 9 manifest variables in the model. We have 22 parameters to be estimated in fitting the model. The number of degrees of freedom associated with this model is 45 minus the number of model parameters to be estimated, 22, and so this model has 23 degrees of freedom associated with it. When we fit the model, we found that the model chi-square value was 20.5524. And so looking at the ratio of the chi-square statistic to the model degrees of freedom, we see that that ratio is 0.8923. Now that is less than 1, and so that would be an indicator of a good fit to the data. Because we have such a small ratio, we expect the p-value to be fairly large, and it is. The p-value for this model is 0.6084. That is quite insignificant. So again, that's a good indication of model fit. The goodness of fit index, the GFI, at 0.9801 is greater than or equal to 0.95, and so that's a good sign. The adjusted GFI at 0.9611 is also greater than or equal to 0.95, and that's a good sign as well. And finally, the root mean squared error of approximation, rounded to 4 decimal places, is 0. That's less than 0.05, and so that's a good thing. And so all of our model fit indices indicate that this extended model does fit the data well. Now let's think about the importance of residual analysis. We extended the model in one place by allowing the manifest variable error terms, E6 and E9, to have a non-zero covariance. Extending the model in this one place made a big difference, converting a model that did not fit the data well into one that fit the data very well. We found the right spot to make this adjustment using residual analysis. And so from this example, we can see the following. All it takes is one entry in the observed sample covariance matrix not being fit well for the fit indices to indicate lack of fit. And because of this, we can see that our fit indices are fairly sensitive to a lack of fit. The extended initial model 1B will be the starting point for our model simplifications. And so let's consider simplifying assumption 1. And so here is a description of this assumption. The variances of the manifest variable error terms, E1 through E9, are all equal, and the variances of the figural relations error terms, D2 and D3, are equal as well. And so here is the null hypothesis to be tested, that the variances of E1 through E9 are equal, and the variances of D2 and D3 are equal. The alternative hypothesis would obviously be that either the variances of E1 through E9 are not all equal, or the variances of D2 and D3 are not equal. And because this or is used in the inclusive sense, it could be that both of those situations are the case. Here is a path diagram for the reduced structural regression model. Notice that we have removed asterisks on D3 and on E2 through E9. And so in this model, there are 13 model parameters to be estimated. And so the constraints that will be imposed on the model are that the variance of E sub I going from 2 up to 9, is equal to the variance of E1, and the variance of D3 will be set equal to the variance of D2. There are still 9 manifest variables in the model. The number of model parameters in this case is 13. The number of model degrees of freedom is 45 minus 13, or 32. The next slide shows the SAS-proc-callus code to fit this reduced model. And so we see, to impose the constraints in the null hypothesis on the model, we equate the variance of D3 and the variance of D2. In addition, we equate the variances of E2 through E9 to the variance of E1. We are imposing 9 constraints on the model, and so this will be a 9 degree of freedom test. Now let's verify that we made the specification of the model to SAS correctly, and we'll do this by looking at the output produced by the model. And so we see here that we do have 9 manifest variables in the model, and corresponding to that, we have 45 moments. Again, the number of moments is equal to the number of non-redundant entries in the covariance matrix. That's given by P times P plus 1 over 2, or in this case 9 times 10, which is 90 over 2, or 45. The number of model degrees of freedom is equal to the number of moments minus the number of parameters, or in this case 45 minus 13, which is 32. And so this information goes along with what we saw previously. And so again, from this part of the output, we see that we have 32 degrees of freedom associated with this model. The chi-square value for this model is 32.6973. And so again, the chi-square value for this reduced model is 32.6973. The chi-square value for what we're calling the full model, which was the extended initial model, was 20.5524. The difference in these chi-square values, which is the test statistic, is 12.1449. And the difference in the model degrees of freedom, which is the number of degrees of freedom associated with this test, is 9, 32 minus 23, and that's also the number of constraints that have been imposed on the model. Here is the SAS code to calculate the p-value for the test. And here's the corresponding output. And so we see here that the change in the chi-square values, again the test statistic, is 12.1449. The critical point for this test is 16.9190, and the p-value for the test is 0.20526. And so this is a 9 degree of freedom chi-square test. The value of the test statistic is 12.1449. We're using a 0.05 level of significance, and so because this is a 9 degree of freedom chi-square test, the critical point for the test is the upper fifth percentage point of the chi-square distribution with 9 degrees of freedom, and that's equal to 16.9190. As we've seen, the p-value for this test is 0.20526, and since the test statistic, 12.1449, does not exceed the critical point, 16.9190, and the p-value, which is 0.20526, is not less than or equal to the significance level that we're using for the test, 0.05, our conclusion is that there is insufficient evidence at the 0.05 level of significance to reject the simplifying assumption that the variances of the error terms E1 through E9 and the variances of the error terms D2 and D3 are equal. The reduced model incorporating these simplifications will therefore be retained and become the model for comparing with the reduced model for the next simplifying assumption that we look at. So in summary, is it reasonable to assume that the variances of E1 through E9 are equal and the variances of D2 and D3 are equal? Yes, it is. Since we failed to reject this assumption at the 0.05 level of significance, it is a reasonable set of assumptions at this level of significance. Let's now look at simplifying assumption 2, which is factorial invariance across time. And so here is a description of this simplifying assumption. Do the latent constructs F2 and F3, the figural relations abilities during the junior year and senior year respectively, impact their corresponding indicators in the same way? That is, are the loadings on corresponding indicators for those two factors equal? That's what it means for there to be factorial invariance across time. Here is a path diagram imposing factorial invariance across time. And so factorial invariance across time implies that lambda 5 and lambda 8 are equal, and also that lambda 6 and lambda 9 are equal. Imposing these constraints on the model, we see that loadings lambda 8 and lambda 9 become lambda 5 and lambda 6 respectively. Note also that we remove the asterisks on those loadings. This path diagram therefore has 11 asterisks, and so there are 11 model parameters to be estimated in order to fit this model. The null hypothesis to be tested is therefore that lambda 5 and lambda 8 are equal, and lambda 6 and lambda 9 are equal. The alternative is that either lambda 5 and lambda 8 are not equal, or lambda 6 and lambda 9 are not equal. To test this hypothesis, we'll fit a model that imposes the constraint contained in the null hypothesis. So the constraints to be imposed are that lambda 8 is equal to lambda 5 and lambda 9 is equal to lambda 6. The number of observed variables in the model is still going to be 9. But now we have 11 model parameters to be estimated. The number of degrees of freedom associated with the model is 45 minus 11, or 34. The next slide shows the SAS-proc-callus code to fit this reduced model. And so we see here that to impose the constraints in the null hypothesis on the model, we change L8 in the model to L5 and L9 to L6. We've imposed two constraints, and so we know that this is going to be a 2 degree of freedom test. So let's verify the specification of the model to SAS to make sure we've done it correctly. We see that we have 9 manifest variables in the model. That's correct. The number of moments is therefore 45. The model degrees of freedom is the difference between the number of moments and the number of parameters, 45 minus 11, or 34. That corresponds to what we see on this slide. And we also see that the model chi-square value is 32.9228. And so let's use this information to test the hypothesis. And so the chi-square value for this reduced model is 32.9228. The chi-square value for the full model is 32.6973. The change in the model chi-square values, 0.2255, is the value of our test statistic. And the change in the model degrees of freedom, 34 minus 32, which is 2, is the number of degrees of freedom associated with this test, as we determined by looking at the number of constraints that we imposed on the model. Here is the SAS code to calculate the p-value for the test. Looking at the output from that section of the code, we see that the change in the chi-square values, which is the test statistic, is 0.2255. The critical point for this test is 5.99146, and the p-value is 0.89337. And so this is a 2 degree of freedom chi-square test. The value of the test statistic is 0.2255. We're performing the test at the 0.05 level of significance, and it is a 2 degree of freedom test, and so the critical point is the upper fifth percentage point of the chi-square distribution with 2 degrees of freedom, which rounded to 3 decimal places is 5.991. The p-value for the test is 0.89337, and so we see that the test statistic, 0.2255, does not exceed our critical point, 5.991, and equivalently, the p-value for the test, 0.89337, is not less than or equal to the significance level used for the test, 0.05. And so the conclusion is that there is insufficient evidence at the 0.05 level of significance to reject the simplifying assumption that lambda 5 and lambda 8 are equal and lambda 6 and lambda 9 are equal. The reduced model incorporating this simplification will be retained. And so is it reasonable to assume that lambda 5 is equal to lambda 8 and that lambda 6 is equal to lambda 9? Yes. Since we failed to reject this assumption at the 0.05 level of significance, it is a reasonable assumption at the 0.05 level of significance. So this completes our model simplification process. Let's recall our parsimonious statement of the principle of parsimony. Everything should be kept as simple as is reasonable, but no simpler. our model simplification process reflects that principle. So let's review the final model. Here is a path diagram for the final model. We see that the variances of the manifest variable error terms are constrained to be equal. The variances of the error terms for factors f2 and f3 are constrained to be equal. In addition, E6 and E9 are allowed to have non-zero covariance, as indicated by the two-sided arrow connecting E6 and E9, with the asterisk indicating a parameter to be estimated. And finally, factorial invariance over time is imposed on the model. Here is the path diagram produced by SAS-Proc-Calus for this final model. The variances of the manifest variable error terms are constrained to be equal, and we can see in this path diagram that their common value is estimated to be 27.59. The variances of the error terms for latent constructs f2 and f3 are constrained to be equal, and their common value is estimated to be 38.97. The loadings on V5 and V8 are constrained to be equal, and their common value is estimated to be 0.9. And the loadings on V6 and V9 are constrained to be equal, and their common value is estimated to be 0.86. And finally, E6 and E9 are allowed to have non-zero covariance, and that covariance is estimated to be 13.38. So we've simplified our initial model. We've imposed several constraints. Let's evaluate the fit of this model. And so we see here down in the right corner of our path diagram, we have a table of fit indices. And so let's take a look at those. First, the modeled chi-square value, 32.92, is less than the modeled degrees of freedom, which is 34. The model chi-square p-value, 0.52, is rather large and it's insignificant. The adjusted goodness of fit index, the AGFI, at 0.96, is at or above the midpoint nines. The comparative fit index, the CFI, with a value of 1.00 rounded to 2 decimal places, is at or above the midpoint nines. And finally, the root mean squared error of approximation, which rounded to 2 decimal places is equal to 0.00, is less than 0.05. And so all of these fit indices indicate that the model provides a good fit to the data. And so let's summarize what we've done. Two simplifying assumptions about this structural regression model were considered and evaluated by performing the appropriate hypothesis test in SAS-Proc-Calus using the model comparison approach. Both simplifying assumptions were considered to be reasonable given the data at the 0.05 level of significance and were therefore retained. None of the model fit indices indicated a lack of fit to the data. The final model appears to fit the data very well. So we've accomplished what we set out to do. I'll see you in the next lecture video.